Yeah, so I'm Ayanda. I work at Erlang Solutions. I'm a senior Erlang engineer, which basically means I've spent a while working with Erlang systems, right? And I'm mostly focused on RabbitMQ, and there's like other languages which I spin off from Erlang, like Elixir, right? And I'm also focused on that as well. So the whole Erlang ecosystem, that's basically what I do at Erlang Solutions, yeah. But more focused on RabbitMQ. And well, this evening I've been invited to come and speak on interconnecting microservices using Rabbit, right? And yeah, we're seeing a lot of use of Rabbit with microservices, and I'm sure this is going to be quite useful for you guys. So, just a question: how many guys have used Rabbit yet? Oh, okay, that's a lot. Okay, so yeah, for those who haven't used Rabbit, this will be like a, just a small intro. For those who've used it, you probably know most of the stuff, but some of it could be very useful. So, so part of my job, right? Well, the main part of my job is I get sent out to different companies, right? And when I get there, I have to solve things. I have to integrate things. I have to put things together, redesign stuff. And one of the most common questions which I get is, well, requirement is we're developing a new system using a microservices architecture, and we want to use Rabbit for synchronous communication, right? So fresh system, something new, and they want to integrate Rabbit into the system. Or, we've got an old legacy system, right? And we're redesigning it and building it afresh, right? So basically taking this old thing, usually in PHP, I don't know why, it's usually systems in PHP, yeah. And we're integrating Rabbit as our messaging bus, right? So you're gonna get Rabbit being used and defined in many terms, messaging bus, queuing system, and yeah, but we'll get into that later. So why Rabbit, right? Well, why the changes in the design before we even touch on Rabbit? So these are the reasons which I usually get from most companies and users. Our system doesn't scale too good, right? We hit the limits of scalability. We don't know how to grow it further, right? Or we're facing performance issues, and things like our system is too slow. Our system is consuming a lot of memory, and we've got all these bottlenecks in our systems. And high availability is another one, where when the system goes down, that's complete disruption of service, right? And it's not easy to maintain. We've got a huge monolith with tight dependencies, So that word monolith, I've come across that word so many times now. I'm like, and much more, obviously, and much more. And I'm sure some of you guys have faced this as well. So, yeah, microservices. So whenever people say microservices, I don't know why, I just picture minions. So, so yeah, so microservices to the rescue, right? And there's a lot of advantages of microservices. There's a lot of documents online. There's a lot of papers which have been written around this area. And just the main, qualities of microservices are loosely coupled. You've got these autonomous micro applications which are totally independent, self-contained, and they're easy to manage. They scale very easily, right? You've got support for multiple technologies, right? You've got a huge organization, one department, they're more comfortable in .NET. The other department, they're like, hey, we want to do stuff in Java. But if it's a microservices architecture, we can all bring those together, right? And and that's a big one, the last one. There's a lot of reduced complexity, right? The more you break up stuff into smaller units, the easier it is to, troubleshoot, for example, if something goes wrong. And you can just focus on that one entity and, resolve whatever the problem will be. And obviously, there's much more, right? You can go and read up on this. So regarding microservices, right, and the whole system design around microservices, I mean, there's a lot of things that you can consider, but I just picked out just 4 main design objectives that we usually look at, right? And just basically, just on the microservice on its own, you'll be looking at building it as efficient as you can, right, in isolation, just on its own. I mean, there's a lot of strategies you can go about this. And different technologies pose different ways of how you can optimize each system. Scalability, right? So when you're designing a microservice-based architecture and system, you have to think about how we're going to scale this, right? And interaction, right? Which is basically where I tend to focus on, right? How are these microservices going to communicate, right? Because, yeah, communication is a big thing in systems design, right? Are we going for low latency, high throughput, right? 100% throughput, or are we happy with like 50% throughput? You know, some messages can fail. You know, some, I mean, they have to always succeed. And reliability, right? That's another key aspect when you're designing your microservices-based architecture. Right, so what is Rabbit? Right, for those who don't know Rabbit, and for those who know Rabbit, this is a bit of revision, right? So yeah, it's an open source message queuing system, right? Licensed under the Mozilla Public License, so free to use. You know, you can just, it's so easy to use. I mean, so quick to use, right? Just download it and install it directly onto your host. It's an implementation of AMQP, right? So the AMQP protocol basically specifies, there's two sides of AMQP. There's the one side which defines how the broker or the server should operate, and then there's the other side which defines the wire specification, basically the transport, right? The payload, the message payload over TCP. How is that going to be formatted, right? So AMQP is quite broad. Yeah, and then Rabbit is basically an implementation of AMQP in Erlang, right? And yeah, and how many people have used Erlang? How many people know about Erlang? Okay, how many people use WhatsApp? Okay, so basically WhatsApp runs on Erlang, yeah. So you are aware of Erlang in a way, right? So, so being based on Erlang, it means it's natively scalable. So Erlang OTP, it's basically a programming language which you know, came out from Ericsson, right, for their telecommunication equipment. And they open sourced it about, 20 years ago, because we just celebrated 20 years of open source Erlang, right? Basically, Ericsson decided to come out with this special technology which they're using. And that's when we started, you know, the community started adopting it for systems like RabbitMQ, right? Systems like WhatsApp, you know, and there's a whole lot more systems that are using Erlang, and you're probably not aware of it. You know, we just got a staggering statistic on how Cisco is using Erlang in their switches, right? So most of the switches that you buy sometimes, you've got Erlang running in there, right? And it's basically been, it emphasizes on scalability, you know, reliability, and you know, there's a whole bunch of attributes which Erlang brings in, which makes it so suited for a system like Rabbit, right? So that's on the broker side, and then on the client side, right? There are more than 20 implementations of AMQP, right? Because all you need is basically client and server, and you need an AMQP compliant client interacting with an AMQP broker. Like Rabbit, an alternative is Microsoft Azure Service Bus, right? And that's on AMQP 1.0, right? So yeah, I think we've got about 20 open source implementations in different languages, and you can just take these, use them in your application, and then I mean, Rabbit enables applications to seamlessly communicate asynchronously or synchronously, depending on the design pattern, you know, which you are gonna take up, right? There's also support for multiple protocols, like MQTT, Stomp, WebStomp, which is basically Stomp over WebSockets, and constrained applications protocol. So if you're gonna go into IoT, you know, Rabbit supports all these protocols. And it's, you know, just in short, it basically allows machines to interact, right? With your applications, microservices, IoT devices, and that is a very, you know, it's actually growing so much. We're finding Rabbit being used to connect all these devices, right? And yeah, this statistic down here, I got this back in 2015, that there were 50,000 known deployments. I'm sure there's way more now, right, of Rabbit. So it's used quite a lot. And in some places which you would never think you'd find RabbitMQ being used, like in the medical field, for example. There's a use case where doctors are now basically during an operation, they're streaming data over Rabbit to remote endpoints, right? So it's being used in a lot of places. And so basically with Rabbit, just in short, you just want to go from one microservice interacting with another microservice, right, over like known protocols that you probably use, REST, SOAP, XML, PC, and you just want to go from that and come to a Rabbit-based architecture where you've got your broker and queuing engine right in the center of your microservices, right? And you've got one microservice pushing messages to the other and the other consuming, and pub-sub mechanism, basically, right? So that's the target. That's the target. And obviously, when you've got more microservices, you'd have something similar to this, right? So multiple microservices interacting over Rabbit, addressing each other and forwarding messages to each other. And then why MQP? So this is just some intro. So MQP is an industry-proven standard protocol, right? It's been around for a while, right? And it started off from companies like JP Morgan, IBM. They came together, they came up with a standard which would basically allow interaction of applications. And it's got a high reputation, obviously, and there's a broad spectrum of primitives that you can use. So it's very broad. You can do a lot of things with MQP, right? And similarly, it's very flexible. You can adapt it to a whole lot of different use cases. And the good thing about MQP, I think this is what I like, is that you control the state of the broker, right? So you can change the state of the server from the client end, right? So basically, it's not just a broker which says, okay, this is my protocol, this is what you can only send. No, it's, I'm the broker, tell me how you want me to be, and, just define my state, right? So that's something which is really good because you get a lot of flexibility with that. And you can actually optimize performance from the client side of your broker, which is quite an interesting feature. Yeah, so that was just intro, right? Just to show you how we are using Rabbit. Well, not really how we use Rabbit in getting microservices to interact. I'm just going to walk through an example, which is, we'll call it a micro mobile network, right? So I come from a telecommunications background, and I've worked a lot with like the core network of a mobile network, right? And services that you find within a mobile network, right? You find a prepaid recharge service, right? Or it could be a department, or you find a VAS processor, which is basically value-added services, right? So like selling stuff over SMS, selling stuff over your mobile, right? So you get all these departments, selling of data, right? When you purchase data over your mobile network, location services, although it's slightly gone down now, but back in South Africa, right, where I worked as a telecoms engineer, there's a lot of location services which are still being used. So 2G and 3G networks, where you've got people forwarding sales and ads based on your location, and basically that location data, they just query it from your mobile network, right? And mobile networks then sell that API to third-party developers, right? So these are typical services that you'd find in a mobile network. Then ESME is just external short message entity. Like if you're a third party, you'd be an ESME. And CDR is just like logs, right? Whenever you get a charge on your mobile, basically it's written to CDRs, right? So we just picture this as our requirement, and we need to build a microservices-based, integration around all these services. And well, I've got other specifications there, but we don't have time to go into how we design for throughput consider message rates, right? So the first thing, so like in any communication system, right, be it radio systems, be it, whichever communication system that you're building, the first thing that you always look at, right, is your addressing scheme. So you just want to come up with a way of, how am I going to interact with this remote endpoint or system, right? And basically with microservices and using them in Rabbit, right, we usually take the name of the service and manipulate that as the address, right? So we basically just map directly into a queue name, right? So remember, Rabbit is a queuing engine, so you've got a whole bunch of queues which are going to be sitting in there, holding messages and passing them on to another application. So usually just come up with an addressing scheme, right? So a naming format, right? So maybe you'd prefix this with, microservice, and then the second entry will be like your department, division, or something in your organization, and then the microservice name, right? And then from this, you come up with your microservice names, right? Or queue names, which you're gonna have in Rabbit, right? So basically, okay, so what I have here, I've got the microservice. So remember I did mention the division. So I've just split this and mentioned the core, because that's like usually in the core network of a mobile network, right? So with this, what we need to do now, we initialize RabbitMQ, right? So you've installed your RabbitMQ node, right? You've got your prepaid recharge microservice, right? You've got your client library in .NET, right? And okay, basically, to initialize, to create a queue is just a matter of three lines of code, right? First, you open a connection, right? So connection open is basically specifying your broker IP, your port, your credentials, right? And after that, this is MQP specific. Once you get a connection, right, you open a channel, right? So what MQP defines is this whole concept of multiplexing connections, right? Because connections are very heavy in terms of resources on your server. So MQP says, okay, if you open a connection, you can reuse that. You can open multiple channels, which each process from your application can use independently, right? And then from there, you just declare your queue, right? So operations like this you'd find in your client application library, right? So basically that'll be it. So MQP queue declare your microservice name, which we've translated to a queue name, and some arguments, right? And those arguments are quite important because those arguments allow us to dictate how that queue is going to operate in the broker, right? So you can actually inform Rabbit that, okay, I want this queue to be durable, right, persistent. I want it to auto-delete, right? When it's no longer being used, just drop it, right? I want to set, for example, message time to live. So if I've got messages and I'm like, okay, this has been sitting here for more than 24 hours, you can just drop this because it's a waste of resources, right? And I can set like max length. There's a whole bunch of attributes that you can set. So like I mentioned, this is from the client side, right? So that's a good thing about MQP. So after that, our microservices have all declared their queues, right? And we've got 6 queues in our RabbitMQ broker, right? Each representing our microservice, right? So that's one step done, all right? And then what would you do next? You'd look at routing, right? So typical communication system, right? But basically in software now. And on your routing side, right, we've got our names, we've got our addressing scheme. Now, how are we going to route messages from one microservice to another, right? So we basically look at the message flow path, right? And MQP has a whole concept of exchanges, right? And an exchange is basically the router within the RabbitMQ broker, right? So a message is basically routed to a queue at the exchange, right? And similarly to our queues, we'd come up with the name for exchange, right? And usually exchanges just pick your departmental name or something, right? So for example, like I mentioned, this is like we're doing something for a core network for the core part of the network, right? You can have microservices which are focused on the radio side of the network, right? So things like, you know, TDM, time division multiplexing applications which will forward traffic to, so you can have those focused on your radio side. And on the core, basically what we're doing now, the billing, the sale of data and all that, right? So you come up with the naming format for your exchange, right? So, and usually what we do is similarly to the queues, you just prefix with a common name, with a common term, basically. So why do we do this? So the reason is RabbitMQ has a concept of policies, right? So if we've got a group of entities within our broker and want to apply a specific policy, we can just apply using a regular expression, which just matches everything which starts with the prefix with an EX, right? So that's just best practice, right? So yeah, you just come up with the naming format for your exchanges, right? And then similar to the queues, you initialize, right? You exchange on the broker. So, which is a matter of just doing an exchange.declare with your channel name, your exchange name, and arguments as well, right? So you can do this dynamically in your application, or you can do this statically when you create your broker. So you don't have to keep on, creating exchanges for each installation that you're going to make. So yes, and similarly, exchanges have also got arguments. You can persist them, right? You can define different types of exchanges. So a direct exchange is basically going to forward messages to the queue that is dedicated to it, right? And then a fan out is just basically broadcasting to all queues which are bound to it, right? And you've got other types like topic, and you can set it to be durable. You can set it to be passive, right? So yeah, there's a whole bunch of arguments that you can set to define how your exchanges are going to be. So yeah, after that, you would have your queues in your broker, and you'd have your exchanges, right? You've got your core exchange, your SIP, right? If you're going to be using some session initiation protocol, radio, and whatever. You can have as many exchanges as you have, as you want in your broker, right? And then, okay, so we've defined our exchanges, right? But still, these guys need to route messages to our queues, right? So what we do next is basically we bind queues to the exchanges, right? So basically, a binding is just a path. It's a named path of how my message is going to go from the router to the queue, right? And usually and these are known as routing keys or binding keys. And we just, best practice is just to use the queue name and map it directly to your routing key. So your root is basically your queue name, because reason being is the moment you bind this guy, right? So the microservice is not supposed to know, this is MQP protocol. It's not supposed to know the queue name, right? So we just bypass that by making the routing key just the same name as the queue. So you specify the path, which is basically the queue name, right? And similarly, it's just a single line of code. And, it's just doing an MQP queue bind or an exchange bind between your exchange and your queue name, right? So once that path is established, you basically have something like this. You have your queues and a whole bunch of paths going to your queues. So now, whatever this microservice forwards to that guy, the exchange can resolve that and forward it to the queue, right? So yeah, that's on the routing. And then, so now we've established the routing internally. And next thing is to establish the communication, right? So we've got our addressing scheme, we've got our routing scheme, and now we want to have our microservices interacting, right? So basically, the whole publish-subscribe idea is, you've got your message transmitter, which is your publisher, right? And then you've got your message receptor, which is the entity that's consuming, right? So all this is specified in MQP, right? So is part of the protocol. How is a microservice or an application going to forward messages in a queue? And how is the application going to consume those messages from the queue, right? And in most cases, your microservice would carry out both. So basically, when you build your microservice, you would add functionality to do both publish and consume from its own queue, right? So yeah, so publish to other queues, microservices, and consume from your own queue, right, to receive messages. And publishing is basically a matter of just doing a simple call, MQP basic publish, and you specify the exchange and the routing key, right? And we did say the routing key basically maps directly to the queue. So that's message transmission, right? And, oh yeah, and all these are reusable, right? So that's why I'm mentioning these as a single line of code, because once you have done this from your queue to clear, you just reuse your connection and your channel. And then consuming is also a matter of just doing an MQP basic consume from your own queue or from any queue in the broker, right? Yeah, and then one thing which you need to bear in mind when you're designing your applications is, and if they're going to interact with Rabbit, is you just want to keep, like I mentioned, each microservice should be able to publish and consume. So you want to keep the publisher and the consumer and the actual part of your application that is actually processing work. Maybe this guy is forwarding messages to, he's inserting messages to database, for example, right? But you don't want this or any one of these to be a bottleneck to each other, right? So the publishing application, the publishing component will be totally isolated. Can be a thread, right? So in Erlang, we've got the whole concept of processes. So it's very easy to actually implement these in Erlang because you just spawn up processes that handle different work in total isolation, right? So that's just one thing that we look at as well when you're implementing a microservice. And yeah, and eventually you would have something like this, right? Your microservices interacting across a Rabbit broker. So if you look at the prepaid recharge, so let's say your prepaid recharge, right, you've just bought, you've just recharged your phone, right? And that charge on your account needs to be recorded to the CDR, to the logs, basically, right? So that entry, you do a publish from your microservice will just do a publish to the exchange, right? And the exchange will just resolve the destination routing key, and from that, it will just forward it to your CDR queue, right? And remember, your CDR microservice is listening and consuming for messages from its own queue. So it will take that and it will write it to file or something, right? So basically, this is the concept. Once you've got your routing, your queues, this is how interaction is going to take place. And at the same time, that prepaid recharge microservice is also listening for messages coming into its own queue, right? And yeah, I mean, you can vary this a lot. You can come up with a whole bunch of design patterns around this, but this is just the basic concept of how you'd establish your communication. And then, yeah, so you've got your addressing scheme, your routing, communication, you know, you can publish, you can consume, but there are some limitations to what we have here, right? And, well, the main limitation is that it's a single node that we're using, right? And what happens if that node crashes? It means all your microservices cannot interact, right? And which is a big problem. And another limitation is, so this is very common, is that a server, a node basically, it can only handle a certain amount of connections, right? Because each connection translates to RAM usage, right? And we get a lot of cases where, you know, maybe people want to connect, you know, like I mentioned, millions of devices which are recording data in remote places, and they're all interacting through Rabbit, and they're like, okay, we cannot add more connections, or our broker is crashing and running out of memory because, you know, we've got thousands and thousands of connections which are established, right? So there's obviously need to scale, right? Oh yeah, and on my laptop, I can only do like 8,000 connections, right? Which is not bad, so yeah. So RabbitMQ introduces the whole concept of clustering, right? And Clustering is just a, 3-command operation, right? You install your new node, and you just stop your current node, stop the application. You join it to the remote node, right? So when I say stop the application, you're not terminating the actual node. You're just pausing the application, right? And then you join it to the remote node, right? And then you just start it up, and you've got a cluster, right? So clustering is very straightforward in Rabbit. And clustering is basically based on the CAP theorem, right? So you've got the flexibility to prioritize what you want more importantly. Consistency, partition tolerance, and there's a whole bunch of algorithms within Rabbit, like pose minority, that you can use to basically dictate how your clustering is going to operate, right? And then you've also got the concept of policies. So once you've got your cluster, right, and your queues, when you apply a policy, right, you create slaves on your remote nodes, right? So when a node basically goes down, right, the slave queue is going to take over processing the messages. So your consuming microservices are never going to experience service disruption, right? Unless it's a rare case where like your whole data center goes down or something. Yeah. So basically that's what you'd have. Your microservices interacting to a RabbitMQ cluster, right? And if any one of the nodes goes down, you have the other nodes operating, which are going to take over service, right? And all this is carried out over Erlang distribution, right? So RabbitMQ rides a lot on Erlang, and it makes things like clustering very easy, right? And yeah, and obviously, ideally, you'd want to front data to your RabbitMQ cluster using a load balancer, So your microservices are just targeting a single IP, and your load balancer is just round robining across your Rabbit nodes. So yeah, and so that would be like your basic installation, right? And your microservices interacting across a cluster. But the other thing is like extensions, right? So you can extend Rabbit from the basic behavior, how it's implemented. You've got a whole concept of plugins, right? And the whole architecture allows you to implement a plugin on your own, right? Start it up within the Rabbit broker, right? And basically, it will change whatever behavior you want to change within the broker. So for example, I've got a LDAP plugin as an example there. So you can actually carry out authentication to an LDAP backend, right? And so these are like part of the standard plugins, which come with the default installation of Rabbit. It's a matter of just enabling and disabling it. And there are also community plugins, which developers just develop, right? And they just contribute to the whole RabbitMQ community, and you can write your own custom plugins, as mentioned. Right, so yeah, you can check this out. These are some of the plugins which I've recently just finished developing, right? So we've had customers saying, oh, we've got some links which terminate, and we want them to automatically restart without us having to log in, right, update stuff, right? So it worked on a watchdog, which is basically processes that have a timer, right? And the concept is quite straightforward. It's just processes that have a timer, and if they detect that something has gone down, they just restart it, or they just carry out some recovery strategies, right? And then there's another plugin, QMaster Balancer. So all it does is so a queue uses up memory, right? So basically a queue translates to resources being used within your node. And what you want to do if you've got a cluster, you want to balance out the location of your queue masters, right? So basically that's what this plugin does. It will conclude that the cluster is balanced if you've got 70% equilibrium across your cluster, right? So So you can also, if you're keen on writing some Erlang code, you can also, work on those. And and obviously security is a big thing, right? Internally, Rabbit has got mechanisms of carrying out authentication and authorization, right? And you can also carry out MQPS, right, between your microservices and your broker, right? And even with your monitoring tools, right? And you've got a whole bunch of security plugins as well that you can enable, right? So like the LDAP, which I've just shown you guys, you've got things like OAuth 2. You can authenticate to remote HTTP backends as well, right? And there's things like the trust store, which is pretty cool because you can whitelist certificates from your microservices. So yeah, there's a whole bunch of security features that you can manipulate within your broker. And then monitoring, right, which is something which is quite important as well. So Rabbit comes with a built-in plugin, right, the management plugin, which consists of the UI, obviously, and you've got an API which it exposes, right? So maybe you're going to see like, tools like, Datadog, Grafana, and all that. You can actually, they basically integrate to the management API and manipulate that. So you're going to see like there's quite a lot of monitoring tools, but they just ride on the management plugin, right? And then we've also got a tool that we develop in-house at Erlang Solutions. It's called Wombat OAM, right? And it's basically designed for Erlang systems, right? And it basically fetches metrics from a remote Erlang node, and which is quite good because you isolate your monitoring tool from your broker, right? Whereas the management plugin, it starts a web server on the node itself, right? So these are tools that you can use to monitor your system. Yeah, so ideally you would have something like this, right? Your microservices forwarding traffic to your load balancer, right? Load balancer forwarding traffic to your Rabbit cluster, right? And a tool like Wombat, right? Fetching metrics and displaying them in your, on your side. So yeah, and eventually, the good thing about Rabbit is that you can expand this. You can expand your architecture without your microservices being aware, right? So if you find there's need to even scale more on your messaging side, you can just add more clusters, add more nodes, right? And yeah, basically improve your messaging layer without any disruption on your microservices. And beyond that, so other things that we do is we do system modeling, right? So if you do have your system, before we actually implement something, would build a model of what you have or the idea that you have, right? Simulate that, right? Do some design strategies for low latency. We always try to attain for 100% throughput. And yeah, we do a lot of performance testing, right? And there's a lot of lower level node optimization. So this is on the virtual machine of the Rabbit node, because Rabbit is basically an application running on an Erlang virtual machine. So that VM, right, we optimize it to suit your needs, right? So yeah, and that's it, right? Any questions you can, yeah, on Rabbit.
Right. Thank you. Any questions?
Yeah, I don't know if you can go back to the slide about the consuming API and the publishing API, because I didn't notice where the message actually was in the API.
Oh, the API. Okay. So basically this.
No, the API itself. The code. Yeah, where's the message? In the publish.
Obviously you'd add your message there. Sorry, I probably left that out.
Okay.
Yeah, sorry.
I was thinking I was going crazy.
No, that's fine. Yeah. Sorry, I left that out. Yeah. That's a typo.
Any other questions? Be there in an hour. Wait, who was it?
So thanks for the great talk.
Yeah.
You mentioned that it provides clustering out of the box.
Yeah.
What happens if I have two nodes running of RabbitMQ and it falls, all of them falls?
Both.
Yeah, and I have to actually get them all both up. So what happens in the middle of that actually if any of the messages are...
So that now depends on how you have your failover strategy, right? So if both nodes go down, like I mentioned, you do get like the drastic case where the whole data center goes down. And there are cases like that, which, from your publishing application, right, you can set things like publish confirms, right? So for every message that I publish, I get a confirmation from the broker. But if I don't get a confirmation from the broker, then my microservices has to do some backup strategy or something, right?
But are the messages backed up somewhere, or are they saved into a disk or something?
So if you look at, if I go to this, if you look at the queues, right? Sorry. So you can set queues to be durable, right? So when your nodes come back up, everything that you had is going to be retained, right? So you can set things like that. So if your nodes do go down and you're using persistence and durability, so when you recover your nodes manually, right? So this is human intervention, and everything that you had in there will be recovered. But messages which are still in flight, right? You wouldn't get confirmations on your application, and you can just back them up. You can have a backup strategy or failover strategy from your microservice.
Okay, so the difference between Kafka and this is that Kafka automatically recovers.
Yeah.
This won't automatically recover. You have to manually
Exactly.
recover each of them.
So, not to be biased, that's why I prefer Rabbit, because I get a lot of flexibility. Whereas with Kafka is always going to persist, right? But Rabbit, for example, when you're working with IoT, right? So devices, if, let's say I need to publish a temperature update, right? If that message fails, it's not a big deal, right? The device can just retry, right? But if I'm now working on a financial system where things need to be transactional, right? I can basically change the state of the queue and the state of the message published to always persist. So for me, that's the flexibility that we get with Rabbit that we don't get with things like Kafka, right? So yeah.
Thank you.
Mm-hmm. Yeah.
Hi, this is again related to clustering.
Yeah.
How is the order is maintained? Especially, is it replication happens between these queues?
Yeah,
which are
exactly.
involved?
So basically, the consensus algorithm that we have running within Rabbit is, let me just get, So if you do apply your mirroring policy, right, you get a ring that's created within your cluster, right? And that ring has got a coordinator process. And then these are basically the implementation internally is Erlang processes, which are maintaining how data is basically stored in RAM, right? If your queue is transient, right, back to your question, and stored to disk if you set it to be durable, right? So it's basically processes which are maintaining how this is going to operate, and they're being coordinated in a ring, right? So if this node goes down, right? So these are slaves. I put them in a bit of a lighter color. So when you're publishing messages, right, all your slaves are doing, they just take copies of what your queue master is getting, right? So you've always got a single queue that is being referenced at all times, right? And your slaves basically are just redundant copies of your master on the other nodes. So if this node goes down with your master, right, the algorithm basically selects the slave which had been alive for the longest. So it's basically, that's the basic concept, but it's more complex, right, when you get into it. But the whole concept is the slave which had been existing for longer, which basically means it's got more consistent data, is going to take over and be promoted to master, right? So that's the concept.
And all the nodes are active all the time.
So if this node were to go down, but all the nodes are always active, right? And so if you notice that, so that plugin which I mentioned, the balancing plugin, right? So all it will do, in this case, it will shift this master and move it to another node. So until you get like masters, a single master on each node, right? Because every time you publish a message to the cluster, right, the load balancer is going to forward it to a random node, or if it's doing round robin or something. And then internally in Rabbit, right, you've got a channel. The channel process is basically going to forward that message to the node with the master. Right? So basically the master is always referenced at all times. Right? Even if the message hits this node and your master is on the other node, the request is going to be forwarded by Erlang Distribution, which is super fast, right, across your node. So that's why I'm saying Rabbit rides a lot on native Erlang clustering, right? So yeah, it's basically Erlang processes interacting across a cluster. Yeah.
Cheers.
Yeah.
Anyone else?
Hi. So my understanding is that clustering is designed to work potentially in a data center as opposed to geographically redundant.
Yeah.
Is there a way to have your messages persisted to an external data source? So if you did lose, say, an entire data center and you needed to come back online somewhere else, if we're talking about cloud or something like that, if cloud provider lost an entire data center, can we persist messages and move them to entire other places?
Yep. Yeah, you can. So, so I've just touched on the basics of clustering, right, which is just the native. But we've got other tools like a shovel plugin or a federation plugin, which every time a message enters a node or hits an exchange, right, it's automatically replicated to another cluster on a different geographical location, right? So when it comes to clustering across different geographical locations, we've got different strategies for that, because this clustering is good, but it works well within the same data center, like you said, same LAN. So where the probability of network partitions is really low, all right? So yeah, there's options like that, and there's plugins to basically intercept a message which is coming in, right? And you forward it to a different database, for example, right? So yeah, it's very flexible, and you can customize it a lot. Yeah.
Last question.
Hi. You mentioned about asynchronous and synchronous usage. Can you talk more about the difference between the client implementations of those?
The client implementation.
Yeah.
So probably just open this. Oh, sorry. Just to explain that. Okay, so based on this, right? If I was going to do, so this is asynchronous, right? I just publish a message, right? If that CDR process decides to send a reply, it will just forward it to that queue. And whenever my application consumes that message, that's when it will process it, right? So it's not waiting, right? But in synchronous, for example, what would happen is this would publish a message, right, and enter a wait loop, right? So each message has got a reference which it can match when it consumes, right? So when you publish, you can wait for a reply to come to your own queue and match for that reference, the message reference coming in. So that's basically how you carry out synchronous operations. It's quite simple.
Okay.
Yeah.
Thanks.
Yeah.
All right.